Welcome to today's webinar titled Identifying Aerodynamics of Small Fixed-Wing Drones Using Inertial Measurements for Model-Based Navigation, based on a paper published in the winter 2023 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is presented by Aman Sharma. Aman Sharma received a Bachelor of Technology degree in Electrical and Electronics Engineering from the National Institute of Technology, Goa, India in 2014. He also holds a dual master's degree as part of the European Union Erasmus Mundus Master on Advanced Robotics at École Centrale de Nantes, France, and at the University of Genoa, Italy, in 2018. He has a short industry experience while serving as a junior manager in the electrical engineering department at JSW Port Limited, India, from 2014 to 2016. He has also worked as a research assistant at the University of Genoa from 2018 to 2019 before embarking on a PhD journey at the Swiss Federal Institute of Technology, EPFL, in 2019. His research has encompassed diverse areas, including biomedical imaging, autonomous vehicles, and motion cueing algorithms for virtual reality gaming. Currently, his doctoral work focuses on identifying and integrating aerodynamics with sensor measurements for model-based navigation. Mr. Sharma is an awardee of the prestigious European Union's Horizon 2020 Marie Curie Fellowship. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. Following the presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We will turn the time over to Aman Sharma.
Thanks a lot, Beth, for the introduction, and a very good evening to one and all from Switzerland. I'm really excited to deliver this webinar on identifying aerodynamics using inertial sensors for model-based navigation. But before I begin, I would like to thank the Institute of Navigation, ION, for giving us this opportunity to disseminate our work to a wider community of PNT. To begin with, drones have become ubiquitous creatures in the modern world. We see them being utilized in various domains, be it cinematography, precision agriculture, medical services, military, and mapping, as you can see on the video here, where you see the snow-covered Alps and the Swiss grasslands. Have you wondered what makes these drones successful for such missions as I'm talking about here? One of the reasons, among others, is navigation. Navigation is defined as the estimation of position, velocity, and attitude of the drone, and this is conventionally done by combining measurements of an inertial navigation system, or the INS, with a global navigation satellite system via an extended Kalman filter, for instance. However, the positioning accuracy of such a system can deviate by a few kilometers within just a couple of minutes of GNSS outage while using small inertial sensors. To alleviate this situation, we can make use of a model-based navigation system. In such a system, apart from using the INS and the GNSS, we also integrate the vehicle aerodynamics to obtain a navigation solution. And this brings me to the outline of today's presentation. I will begin by first presenting some background on model-based navigation, followed by the identification algorithm, and in the end, the experimental results. So let's start simple. As I said earlier, a typical integrated navigation system, it consists of a navigation filter. And in this filter, the process model or the state dynamics are actually driven based on an inertial navigation system. On the other hand, sensors like GNSS serves as external observation And this is basically used in the update phase of the filter. When we transition from this integrated to a model-based navigation system, first and foremost, this integrated navigation system is replaced by something that is called a vehicle dynamic model. I'm going to come to the vehicle dynamic model in just a bit, but a very important distinction here is that both the IMU and GNSS, they serve as external observations in this setup, and this vehicle dynamic model is a function of the autopilot control commands, the wind velocity, and the aerodynamic model parameters. And if these parameters are correctly set, we can see in the state of the art that the model-based navigation system outperforms the free INS by 1 to 2 order of magnitude. However, there is still a question that is not very well answered within the state of the art, that is how to set these unknown model parameters. And before we can even start going into the question and realizing its importance, it's important to first understand some mathematical background. And in the next couple of slides, I'm going to talk to you about that. And again, let's start simple with some equations and framework that most of us in the navigation framework know of, which is the integrated navigation system. And the state dynamics of the system is represented by the following system of differential equations. Here in this system, the unknown states here are the position, which is expressed here in this case in the Earth-centered, Earth-fixed frame, and then we have expressed in ellipsoidal coordinates, just to be more rigorous. Then we have the velocity in the local level frame, the attitude, which is represented here in using quaternions, and then we have the IMU error states, which for the purpose of simplicity, here are modeled using a random constant. More involved stochastic setup can also be used. And an important factor here in the system of differential equation, the specific forces and the angular velocity are the forcing inputs. These are the forcing inputs to the differential equations. And when we move to a model-based navigation system, something changes. Well, first and foremost, we make use of models of specific forces. And additionally, we also include a model of moments into the picture. It's not pure dead reckoning as we know from the integrated navigation system. In addition to this, there are two important factors that are also included, which I'm highlighting here, is the wind velocity in the local level frame and unknown aerodynamic parameters. Now, before we go a little bit deeper into this, let's try to first understand about these forces and the moments. So what are they? These are the aerodynamic forces and moments that are experienced by the drone during its interaction with the incoming airflow. It's just not its interaction with the airflow, but also when the control surfaces and the propeller is moved, how does it react with the airflow and by itself? So these are captured by the forces. For instance, these forces can be categorized into the thrust force, which is predominantly based on the propeller. Then we have the drag force, side force, lift force, and we also have the three moments: the roll moment, pitch moment, and the yaw moment. Now let's go one step deeper into this. So when we look at a model for the vehicle aerodynamics, we see that it's really complicated. And to make things easy to understand, let's look into it in a stepwise way. First and foremost, these forces and moments are functions of certain geometrical parameters. This includes the diameter of the propeller here. S is the wing surface here. And then we have B is the wingspan. C bar is the mean aerodynamic chord. In addition to this, it's also a function of certain control inputs. These control inputs include the speed of the propeller, n, the deflections of the ailerons, delta A, deflection of the elevator, delta E, and the rudder deflection, delta R. Then we have certain parameters or variables associated with the dynamics of the drone, and this is captured by the non-dimensional angular velocities, which are pointed here. And then we have some entities related to the wind, and we see that V is the airspeed. Then we have the angle of attack and side slip angle. And then comes the part that we are mostly interested in, are the unknown model parameters that we need to find. So how are these parameters calculated or estimated? In general, in the state of the art, we have two approaches to do that. One is wind tunnel experiments, and the other are computational fluid dynamics simulations. However, these approaches are expensive and also time-consuming in some aspects. On the other hand, we are proposing something completely different. We are trying to use inertial sensors to obtain a value of these for model-based navigation. And the premise of our work is based on the observation model of the IMU. And this model, without going into the details, first is nonlinear, which is not very interesting for estimation theory. And it's nonlinear with 21 unknown parameters that I showed on the previous slides. And then there are 3n unknowns for the wind. As wind is time varying, if there are n observations for the IMU, we consider 3n for the wind. What we show in our paper is that this nonlinear problem can be broken down into 3 separate linear estimation problems if these estimations are carried out sequentially. And what estimators am I talking about here are first the wind estimator, followed by a moment parameter estimator, followed by the force parameter estimators. All of these estimators are making use of the flight data that is available for free. This data includes the pitot tube for the airspeed, autopilot control commands for the deflections of control surfaces and propeller, the GNSS, and IMU. Once we have all of this data, we can actually execute these estimators. So before I go a little bit deeper or briefly deeper into these estimators, it is important, and I repeat, it's important to understand that this estimation is carried out offline by recording all the available flight data, and all the 3 estimators share commonalities, and they all are working in a similar way. First and foremost, all these estimators have a similar structure where the state dynamics is linear and time invariant, whereas the observation model is linear but time variant. And once we have the structure, we are then computing the observability gradient of this system in an iterative manner. Then what we do is we are trying to track the eigenvalues and the eigenvectors of this observability gradient. And as this is a positive semi-definite matrix, we expect that the eigenvalues are gradually growing in terms of their magnitude. And then based on the magnitude, or what we are actually interested in, as we will also see later, is how much are they growing? Is the growth significant for us? And based on this, we use something which is called a partial update framework. This framework was originally proposed in the paper that is mentioned here, wherein and I will come to the paper, I will come to this concept in just the next slide. So in general, an estimator consists of or is trying to estimate the unknown, which is the state, based on some observations that it is receiving, and these observations are certain kinds of measurements that it has. And of these states, there are some states that are observable and some are not observable. The problems that were discussed in the paper are, if these unobservable states are updated in a traditional setting, this can cause inconsistencies and can lead to filter divergence. On the other hand, if they are completely ignored, this can lead to erroneous estimates. So it is important for us to discern the observable states from the unobservable states based on the observation that we get. And we will actually show this more in a practical setting in a while, because when the drone is flying, there are certain maneuvers that make certain entities more observable than the other, but then there are some other maneuvers where we can get some other information. So the idea is to selectively update some of the states that we want to know and ignore the rest. And this criteria to decide is based on the observability gremlin. If there is a significant growth in the eigenvalues of the observability gremlin, then we would like to update the states. Otherwise, we would not like to update. Well, putting all of this in the context, in a real context, an application-oriented context, we can divide the thing into two different phases. One is a calibration phase, wherein we record all the data, we plug it into our wind moment force estimators, we obtain the model parameters. Once we obtain these parameters, we have a test flight, and we plug this into the VDM EKF framework to get a navigation solution. Please note that here we are using our method to have a priori values of model parameters. However, we can also have some other methods, for instance, the wind tunnel in this case, to initialize these parameters. Now let's look at the experimental setup. We make use of two drones for this setup. One is a fixed wing drone, a conventional fixed wing drone, and the other is a delta wing drone. These drones have their own autopilots, and in addition to that, we also have two different payloads that consist of the IMUs and some other electronics and hardware for the purpose of data logging, time synchronization, and others. Then these drones have their own GNSS receivers. In addition to this, we have also installed a base station where we record the data, which is later used for PPK. Once we have the PPK data, we combine it with the inertial data obtained from the IMUs, and using an optimal smoother to obtain a reference navigation solution. And this solution is used for the calibration, and then later on to validate the method to judge the navigation drift that we are obtaining. So let's actually start with some results now. First, let's begin with the wind estimator. So wind estimator has 4 states, the 3 related to the wind, and one is a pitot scale factor. And in blue here, you see the growth of the eigenvalues of the gremlin. And since the plane in the beginning is making quite a lot of maneuvers, we see that there is some growth along all the possible bases. And then when we start the mission, well, the mission kind of starts in a north-south oriented fashion. So we have more growth of the eigenvalues along this basis. And then when the plane starts to have some maneuvers in the east-west direction, then we have more growth here and almost nothing on this side. And at the end, we have a picture that looks more or less like this. So what we are going to do now, so these represent the incremental growth or the growth of the eigenvalues during the different maneuvers of the flight. And we are trying to understand the observability of some of the elements of the wind estimator here. So if we correlate this particular growth of eigenvalues with the airspeed measurement that we get, we see that first there's always some growth, and it's correlated with the airspeed, and this goes very consistently with the existing state of the art that says that the pitot scale factor is always observable as long as the drone is airborne. Then, if we look here, we try to compare the growth of the two different the growth along two different eigenvectors and correlate it to the yaw. Instead of airspeed, here we have yaw, and we see that these two are correlated, but in a complementary way. This is to say, a growth here would actually mean a fall on the other hand, but still they are correlated. And this is, again, consistent with the state of the art that says that in order to estimate the wind, the drone needs to make several turns so as to make the horizontal wind observable. And in the end, we see very little growth of the eigenvalues in this particular case, which is correlated to the pitch in this case. And this is again consistent by saying that the downwind is less observable than the horizontal one for a fixed wing drone. This is nice. Well, we were dealing with a state space which was 4-dimensional. But as we move to a high-dimensional state space, for instance, for the moment estimator, which is 11-dimensional, making these one-to-one correspondences is hard. And therefore, what we do here is we try to present some of the top few points of the trajectories where we saw the most amount of the growth in the eigenvalues. And if you look at this graph carefully, you see that the red portions, which amounts for more observability, are actually happening when the drone is making turns. And this again validates the point that the observability, the parameters are not always observable. They are only observable when the system is well excited. So once we have obtained all of these parameters, we put these parameters in the VDM based navigation filter, and we can see that and we introduce a 2-minute long GNSS outage, and we see that the performance of the model-based system in green is much better than that of the conventional FreeINS in red. But now I would like to raise some curiosity that does this really make sense? And to answer this, we did some kind of an adversarial testing. What do I mean by that? Is that we tried to randomly initialize these aerodynamic model parameters with some random values, and in most of the cases, we actually encountered some numerical instabilities that led to a software crash, and so we didn't get anything. But we were able to find 2 different cases where it actually worked. It worked in the sense it gave some solution, but that doesn't mean that this solution actually makes sense. So if you look here, there are 2 different solutions, and both of them during the outage are going nuts. And this again proves that it's important that those parameters actually make some sense, and only if we have some coarse estimates that are good enough, then the model-based system will work better. We tested this again with a different scenario, which is using a delta wing drone. And for a delta wing drone, the aerodynamic model is far more complicated. That was available in the state of the art, which has 44 unknown parameters. And when we look at the performance of the model-based system in black, it looks kind of better than the one in red, which is from the FreeINS. but the performance factor is not as good as we saw in the previous one. Well, there can be many reasons to this, but one of the main concerns that we have based on this particular work is that it seems that the model in red is overfitting the data in blue. Whereas if you look for a fixed wing drone, it seems that the model is kind of filtering over the data that is present. So in short, there is a need for a better model for a delta wing drone. With this, I come to some of the impacts of aerodynamics identification, or the impact that this work has had. First and foremost, I'm happy to announce that thanks to this identification algorithm, we were able to develop a real-time navigation system in which we were able to fuse the data of INS, IMU, GPS, and the aerodynamics for two different drones, and we have actually presented a real-time architecture to do that. If you're interested, you can look into this work. And at the same time, there are many other applications that we are currently exploring, and maybe this can go more in the discussion part. And with this, I would actually like to bring my presentation to a conclusion. So what I would say that we have tried to identify the aerodynamics using only inertial sensors, as opposed to the existing methods that really rely on wind tunnel experiments or fluid dynamic simulation. At the end, I'm also thankful to the European Union Horizon 2020 program and Swiss National Science Foundation for funding this research, and ION for giving us this opportunity to disseminate this work to a wider audience. And with this, I shall close my talk. Thank you.
Thank you, Aman, for this great presentation. We will now accept questions from the audience. As a reminder, you can submit your questions using the Q&A button in your viewer. And it looks like we already have some questions coming through, so we can begin with, can you discuss model overfitting for the Delta Wing drone in this presentation? And what is the reason behind it, and how can this problem be addressed in the future?
That's a great question. So there are a few aspects that were not discussed entirely in this presentation, but are present more in the paper. First and foremost, the identification method has made use of some existing functional models that exist. So for instance, for a fixed wing drone, we see that these models are polynomial based with 21 parameters, whereas the one for the delta wing drone that we have seen consists 44 parameters, and there's only one work that is present. So there has not been extensive there was not extensive testing that was done on the model itself. From an estimation point of view, yes, the estimator was doing the job as it should do, but it was overfitting. I'm also happy to announce that in collaboration with one of my colleagues here at EPFL, we have actually tried first to get a functional model structure for a delta wing drone. And this was done using wind tunnel experiments. And then when we have these functional model structure, we completely forget about their numerical parameters, their numerical values. Rather, we use our algorithm, the WMF, to obtain the values of these parameters, and we test and compare the two methodologies. Well, I can't say too much about it because this work is currently under review. But what we see that there is not a huge difference in between the performance of the two methods. They both perform very well when we compare them in terms of GNSS outages of up to 3 minutes. So in the future, we could probably use a simpler model which has less number of parameters and still make use of this method.
Okay, great. We have another one here. Can you use truth data to fine-tune the parameters of the vehicle dynamics model for the specific vehicle you are using?
So I'm assuming that the truth data you mean are the true values of the aerodynamic model parameters. If I'm wrong, you can probably tell us later. There are some interesting facts about this, because when we do wind tunnel experiments, the plane or the system that, or the estimators that we are, or regression that we are doing, is only seeing the data when we are doing those experiments. And when the drone is flying, there are far more interesting or different factors that are actually affecting the forces and the moments that are experienced by the drone. So yes, if you have the truth values, as you say, the truth values from wind tunnel experiments, it may not be fully representative of what's going to happen in the real flight. And that is also one of the reasons why we put them in the state vector, so that they can be slightly fine-tuned while the drone is flying. However, if these values are completely off, as I was speaking in one of the slides, the drone can go astray, or the software filter that you use can crash. So yes, those values are really important, and those truth values can be used.
Okay, we have someone else who says they've not yet read the paper, but that it looks like you have 3 stages for your estimator. So how did you determine the order of those 3 stages? And how did you ensure the estimated parameters are consistent over different data sets to avoid local minimals?
That's a very good question. So the order of the estimator, well, it's important to understand that I have not discussed this again during the presentation, but the nonlinear model for the IMU consists of 21 plus 3n number of unknowns. However, there are more equations that are used, and what we see is that there is one equation that I presented, and there is one more equation for the moments, which was not shown in the presentation, but you will find it in the paper, which has 11 unknowns for the moments and 3 unknowns for the wind. So the key point that we have found out by seeing those equations is, if wind is estimated a priori, then that moment equation that I was talking about, which has 11 plus 3n unknowns, becomes linear in just moment parameters. And this is already a good step. So we have already covered 2 steps. That first it has to be the wind, then it has to be the moments, and finally the last equation has 21 plus 3n. So if both the moment parameters and the wind is known a priori, then the equation that I presented earlier would become linear in force parameters. And therefore, once it's a linear estimator, we can actually get away from this concept of local minima, as the problem no longer remains nonlinear, and we don't have to have some kind of an initial guess to start the process, and also we don't have to use multiple iterations. Now, coming to the second question, which is more interesting, is how did we validate this? So overall, well, in the paper we have presented some of the flights, but there are more works. For instance, where we have validated this setup, but there are more works that are published or are coming soon, where we have, I think, more than 7-8 flights in total where we have validated this framework, the same model parameters in real life, including the 2 flight tests in real time.
Okay, and it looks like we have one more question here. Could neural networks be augmented to the known vehicle dynamics model to help improve the unknown portions of the model?
That's a good question. However, since I have not done any background research on the use of neural networks for this particular application, which is involving real-time navigation, I am not able to answer it at the moment. I'm sorry.
Okay, it looks like that's all we have for questions. So we just want to thank everybody for joining us today for today's webinar, and thank you, Aman, for your time and preparation. We want to remind everyone that a recording of this webinar will be posted to our website, YouTube channel, and our social media channels by Monday the 4th. So thanks again, and we look forward to having you all join us for a future ION webinar.